we can do is to introduce neural networks and then depending on you we can I can, because we do not have enough time, I can introduce to you one type of neural network. Okay, so neural network are approaches which can be used mainly for supervised modeling, so to do both regression or classification. Okay, and they are not new actually. Okay, now they are very trendy. Everyone is speaking about neural networks, but the first idea to develop neural networks dates back to the 50s. Okay, so 70 years ago. Okay, so they are actually very old. The problem is that they require a lot of computational power, and at that time, and also they require a lot of data. Okay, because the idea is that you mimic the human brain and how the human brain learns information. Okay, so in order to train neural networks, you usually need a lot of data, so a lot of samples. Okay, to have a good learning, and this means you also have you also usually need computational power. Okay, so 70 years ago, people do not have data, and they didn't have computational power. But in the last years, as you know, okay, we got a lot of technology. So we got a lot of possibilities to improve the computation. Okay, and also we got a lot of data from internet. So this is why now there is this boom of applications about neural networks. Okay, but the idea, the original idea, is not new. Okay, so the idea is to simulate somehow the brain, the human brain, to learn information. Okay, of course, our brain learns information looking around. Okay, and having information from the surrounding environment. For neural networks, I mean, neural networks learn from the data, okay, you give them. And they are called neural networks because, I mean, as in our brain we have neurons which are connected. So we have a network of neurons, okay, which are connected and share information. It's exactly the same. So neural networks are made by neurons, which are the unit, okay, of the network. And these neurons, they share information. Okay, so you input some information from your data, and then this information is transmitted and shared by the neurons. Okay, and in this way, the network learns information from your data. This is the idea. Okay. And you can do that in many ways, because there are many ways that you can arrange these neurons. Okay, so you can organize these neurons with different architectures. This is the technical name. And so neural networks can have very different structures. Okay. And this is the mess, because then which structure do you need? You need really a lot of, in my opinion, a lot of experience to understand which structure you need, and also a lot of time to tune, okay, to optimize the network. Okay, this is why it's not so, I mean, it doesn't make sense to use neural network if you have an easy data set that you can classify with discriminant analysis, okay? Because it requires knowledge and time to be used. Okay, so I don't know if you have ever used or heard about songs, which means self-organizing maps. Have you ever heard about that? No? No? These are also called cohonent maps. I never remember what is each. Okay. Have you ever heard about that? Cohonent maps? Cohonent was the inventor. He was a Finnish guy. He was the inventor, I think, in the late 80s of this kind of neural network. Okay, self-organizing maps, which is again an architecture of neurons, okay, which share information. With this neural network, you can do everything, because you can do regression, you can do classification, but you can do also data exploration. So these are used also in an unsupervised way to do data exploration, like PCA. Okay. So if you want to see if you have clusters in your data or whatever, okay. These methods are also used for that. Okay. Another type of neural network are the feed-forward backpropagation neural network. Have you ever heard about that? Or better, call it backpropagation, okay? It's better. Have you ever heard backpropagation? Okay. So, we have time just to see one of these two. Do you have any preference?
First one?
Or I decide? This one? Or this one? I mean, we can do both, but it's, what time is it now? I don't know if we have enough time. Let's start with this one, and then if we have time, we do just an introduction to this. Okay? Okay. No. If it gets complicated, stop me and let me know, okay? Because also, I mean, it's the first time, because these slides are new, so it's the first time I use this kind of slides to explain these things. So let's see how that works, okay? So, as I said, okay, what we do is to try to mimic the human brain with an architecture where you have neurons, okay, which are the units which constitute the network, okay, of the neural network. So you have a network of neurons which communicate and share information, okay? How they do this? How does it work? Okay, how does it mean that they share information? Okay, so I said to you that of course we need some data as an input. Okay? So as usual, you have your data matrix with samples and variables. Okay? And these samples then are given to the network to learn. This process, okay, is divided in two phases. Okay? First, we have what is called forward propagation. Okay? So just imagine that we put the information, okay, in the network, and this information is propagated to the network, and we will see how. Next, probably after lunch, then we will see the opposite, the second step, which is the back propagation. Okay? Because the information goes and then comes back. Okay, so it's a process which is constituted by different steps. Okay? So, imagine, okay, in this visual representation, okay, that this circle is a neuron. So one of the units which constitute the network. Okay? And imagine that we have our data, our input, okay? Just to make a simple example, let's say that we have just 3 variables in our data set. Of course, then we will use much more, but just to start, let's say that we have 3 variables, okay? So this is one sample, right? It's a sample, okay, which is a vector of values with these 3 variables. This, okay, variables, okay, this is the input for the neuron, okay? And somehow, we will see how, the neuron is able to process the information which is contained, okay, in these variables. How? It uses a logistic function. Do you know logistic regression? Okay. That's the basis for neural networks. Okay? Then, this is just the general, okay, type of neural network you can have. Okay? And here you have the this logistic function. Of course, then there are, you can modify, everything I'm explaining then can be modified, okay? Having different types of neural networks. So I'm just explaining the general approach, okay? So, this is a logistic function, okay? How does it work? It's also called an activation function, okay? It's the function which is used to get the information from the variables, okay, to the neuron. Here you have a linear combination, okay? If you know logistic regression, this is a linear combination of your variables, okay? Where V, can you see it? Yeah. Okay, this is your sample with 3 variables, and then you have this, okay? And you do a linear combination between X and V. So, usually, these are called coefficients, okay? When we did super vector machine or PLSDA, okay, these elements of the linear combination are called coefficients, right? Here, in the neural network language, okay, they are called weights. Okay? So the weights are the coefficients of this linear combination, okay, between the input, okay, and the neuron. Okay? So, look at the logistic or at the activation function, at the logistic function, if this linear combination, okay, is higher than 0, then you get an activation function which is higher than 0.5, right? And it tends to 1 if the linear combination is very high. On the opposite, okay, if this linear combination is lower than 0, then you get an activation function which is lower than 0.5. And if this linear combination is very low, then you get an activation function which is close to 0. Okay? Okay. And this is the logistic function, okay? It's this one. Can you see when the linear combination is equal to 0, then this is equal to 0.5. Okay? Okay, so we have some weights that, how can I say, govern, okay, with a linear combination and then with this transformation, okay, they govern the input of the information in the neuron, okay? Now, we have the weights, okay, which are associated to our variables, but usually we also have a bias, okay, which has to be considered in this linear combination. It's like the interceptor, right, in our linear models, okay? You have also it here. So this represents the bias, okay? Where this x0 is usually equal to 1, okay? And it represents the bias. It's the same in linear regression, eh? Okay, so actually we have 3 variables, okay? This is the input vector for our sample, where this is equal to 1, and this is the set of weights that we use to get this linear combination, okay? Now, this is just one neuron, okay? But in a network, we have many neurons, right? So, usually, you have neurons which are organized in this way. So, again, here you have our sample, which is the input vector, okay? Of course, I mean, here we are, now I'm simplifying things. We have just one sample, but of course, if we have a data matrix with 1,000 samples, then these samples are presented to the network one at a time, but we will see it later, okay? So just imagine we have one sample, okay? These are the 3 variables, okay? In the terminology of neural networks, this is called the first layer or input layer, okay? Then you can have, of course, a network of neurons, because they have to be a network and they have to communicate each other, okay? And these neurons are organized in layers, okay? So for example, in this very simple example, in this case, we have 3 neurons in this layer, and then here we have another layer with just 1 neuron, okay? This last layer is called the output layer, okay? So it's the end of the neural network. It's where we get the output from the neural network. So you have some input, then the information is processed by all the all the neurons in the hidden layers, and then you have an output, okay? Where we get, for example, a prediction. So, input layer, output layer, and this is the hidden layer, okay? Where we have 3 neurons, for example. In the output layer, here we have 1 neuron, but we can have more, okay? And here we have 3 neurons, but we can have more. And we can have more hidden layers. So here in total we have 3 layers. Input, 1 hidden, and 1 output. But you can add, you always have 1 input layer and 1 output layer. Those are fixed. But you can have more than 1 hidden layer, okay?
Didn't you say that the output layer can be more than 1?
No, the neurons in the output layer can be more than 1.
But the layer, okay,
one.
yeah, okay.
But you can have more hidden layers. And if you have more hidden layers, then you are doing deep neural networks. Okay? So when they talk about deep neural networks, it means that there is more than 1 hidden layer. Okay. So you can do a very easy network with 2 neurons and 2 neurons, and you can say, I'm doing deep learning, okay? Right. People do that in my opinion, but okay. Now, can you see all these arrows, which looks so crazy? Okay. They are the direction where you have the forward propagation, okay? So, you remember here we have, for example, 1 neuron, okay? 1 of the units. And can you see it gets information from the input layer? And here we have, so here we will have the activation function with the logistic function for this neuron, okay? So here we will need 3 weights plus the weight for the bias, if you consider the bias, okay, to get the linear combination to get the activation function. So this is the activation function of the first neuron in the second layer, which is the hidden layer. The same here. Here we have another neuron, and so we will get, with 3 weights, we will get a linear combination of this input to get the activation function for the second neuron in the second layer. The same here, but then here we have another layer. In our case, it's the output layer. And so look, here we have another activation function. Okay, if you understand this step, then you understand neural networks. Here we have another activation function, which is a function of these 3 inputs. So again, we will do a logistic, we will use a logistic function with a linear combination of these 3 input, which were the activation function of these neurons. So we will do a linear combination of these 3 activation functions with 3 weights. And we will get this one, which is the activation function for the first neuron, the only neuron we have in the 3rd layer, which in this structure, in this architecture, is the output layer. Okay? This is how the information is propagated. Okay? Which means that here, okay, we need the weight to each arrow. I mean, for each arrow you have a weight, okay, to control the information here. So here we will have some weights, okay, which define how the information goes from the input layer to the hidden layer. And here we will also need some weights to control how the information goes from the hidden layer to the output layer. Okay? How many weights we will have here?
Three.
3. How many here?
9.
9. Okay?
But, sorry, David, but the bias has a weight. Okay.
Good question. Okay? So, you also have bias. Okay? And so you also have to consider bias when you have this linear combination. I missed 2 arrows here, okay? I have to put them. Okay, so you have also the bias here and the bias to this last neuron. Okay? It was a mess to do these slides because it was full of errors. Okay? And of course you also have the bias here. This is a bias. Okay? Because again here you do exactly the same, but you use as input these activation functions.
Question, shouldn't the variables x1, 2, and 3 be connected to the activation? Yeah.
No, because this is just a bias, so it's a fixed value.
Okay.
Okay?
So that's why.
It's equal to 1.
Okay.
So you don't, actually, it does not receive any information. Okay? So, okay? So in this phase, okay, you have forward propagation, which means that you input the information. And can you see all the arrows are in this direction? So you input the information and then you go through all from the input layer to the hidden layers, 1 or more, and from the hidden layer to the output layer. So you have this propagation of information. Okay? I hope you, now let's see in details, okay? Not in details, but better, how does this information is propagated with the logistic activation function. Okay? So, imagine we have this neuron. So it's the first neuron in the first layer, right? Now let's do this without bias, just to make things a little bit clearer. As we say, we have a logistic function, which is this one, do you remember? Okay? Which is based on the linear combination of the input and some weights. This weight is the weight, okay, for the first layer, which control the first input to the first neuron, okay, and so on. So we have 3 weights, as you said before, okay, and this is the linear combination, okay, x1, x2, x3 with the 3 weights, and this is the bias. Okay, so here you have the bias. I didn't put it here, just not to have too many circles. Okay, so with this linear combination and with this transformation, then you get this activation. Okay, so this is the activation function for the first neuron in the second layer, which is the hidden layer. Okay, then we do the same for the second neuron. Okay, of course the weights will be different. Okay, and so this will be the linear combination. Okay, x1, x2, x3 are always the same, it's the same vector. But now with different weights we give a different kind of information to the second neuron. Okay? And we get this. F again is the logistic activation function. As you can imagine, the same for the last neuron. Okay? So we have a linear combination with different weights. Okay? So, this is just a representation of what we have seen so far. It's nothing new. Okay, these are the three activation functions that we get for the neurons in the second layer, which is the hidden layer. Okay? And these are all the linear combinations. Okay? So you can collect all the weights that govern this activation, okay, in this matrix. Okay? We have the weights and also the weight for the bias. Okay? So, here we have a matrix which has dimension 3 times 4, because the number of rows corresponds to the number of neurons you have in the layer which receive the information. The number of columns, okay, corresponds to the number of unit, okay, you have in the previous layer plus 1, because you have the bias also. Okay? So here we have 3 inputs, okay? And so this matrix will have dimension 3 columns, the number of neurons here, times 4, which is 3 plus 1. Okay? And these are all weights that, okay, connect the input and the neurons. Okay? So, I don't know, VU221, okay, if you look at this terminology, means that this is the weight, okay, in between the first and the second layer, okay, which connect the second neuron, okay, here, with the second input variable here. So this arrow, for example. Okay? We will have something like this also in between the second layer and the third layer. In your opinion, which will be the dimension of that matrix? We can call that matrix with the same terminology, VU2. Okay, so these are the weights, okay, which govern the transmission of information between the second layer and the output layer, the third layer. Okay? Which would be the dimension in your opinion? Remember, the number of rows is equal to the number of neurons you have in the layer which receive information. So 1. And the number of columns is equal to the number of units you have, neurons here, in the layer that sends the information plus 1, because you have the bias. So that would be, it's not a matrix actually, it's a vector with dimension 1 times 4. Okay? Okay, and this is what happens. Okay? Can you see now the idea? Because, okay, now we started from the first layer, the input layer. Okay? From the input layer, we activated all these neurons. Okay? And we got these activation functions. Then, now, the propagation goes forward, okay? So, from the second layer, the hidden layer, we go to the last layer, which is the output layer, okay? Here we have just one neuron, okay? So, this neuron, we will get an activation function, okay? Which will be based on what? The linear combination of these three, okay, with some weights, okay, plus the bias. It's exactly the same. So again, we use a logistic function, okay, to get this activation. Okay? That's all. Of course, here we have just one hidden layer. You can have more hidden layers, more neurons, and you have the transmission of the information which goes in this way through the network. Okay? And so can you see there? I don't know if I put it in the slides. Yeah. Okay? We say that the weights, the matrix of the weights between the second and third layer has dimension 1 times 4, and this is the one. Okay? If we had two neurons in the output layer,